And for the very last time, welcome to Foundations of Algorithms. Again, I am Dr. Shanan Connie, and it has been an absolute privilege to have all of you in my class this semester. So it would not be Foundations of Algorithms without one last historical figure. And here we have Richard Dick M. Karp, who is now 90 years old. He was born in 1935, and he is a Jewish-American computational theorist. So again, adding another layer of diversity to the people that we've seen that have contributed to the field. Now, the area that Dick Karp is particularly known for is the contributions to the theory of algorithms, and in particular complexity theory, which we will talk a little bit about today. Now, like all of our other figures, he did win a Turing Award, and this was for studying the fundamental complexity of algorithms, not just for specific algorithms, but about how algorithms as a whole behave, and as well for the development of the notion of polynomial time, which we will discuss in this class. I think currently, by memory, he is still affiliated with UC Berkeley despite being 90. So if you are a professor and you've contributed a lot of your life to an institution, you become what's called an emeritus professor, which is they're not paying you anymore, but you get to keep an office, you get to keep advising students, and you're essentially a member of the walls of the university, standing there essentially until you pass away. So with that, where we left off last week was looking at categorizations of different types of algorithms. So it looked at generate and test, and another type of algorithm that we have already seen in this class pretty frequently is divide and conquer. So this was the strategy of taking a problem and dividing it into smaller subproblems and keep continuing this division until we got down to the level where we had subdivided the problem sufficiently such that we could solve a very simple instance of it. Now, does anyone remember some of the algorithms that use this paradigm? Aaron, do you remember any algorithms that used divide and conquer?
Merge sort?
Yeah, merge sort is the prototypical divide and conquer algorithm. What about some others? Anyone else remember? Another divide and conquer algorithm? Danny?
Quicksort also does it, but in like a slightly different way.
Yeah, quicksort also does it in a slightly different way. So we have a couple of algorithms that we've used. Binary search, as well, this idea of breaking problems into smaller and smaller pieces. So in binary search, we divide into half again, divide it into half again, until we could solve a smaller version of the problem. We also did this with our longest common prefix problem. And we will see this once more at the end of class with the nth Fibonacci problem. Aaron.
Would the Towers of Hanoi problem be considered a divide and conquer?
Yeah, Towers of Hanoi is also conceptually, in a way, divide and conquer. But essentially, the idea we had with the Towers of Hanoi was, can you solve the one disk, the problem of moving one disk to another pole? And if you can solve the one disk problem, how do you do that with two disks? Then you build that up into how do you do that with 3 disks, 4 disks, all the way to n disks. So I've talked a lot about this paradigm before, and so we're actually not going to talk much more about it today. Hopefully this is one of the concepts that you have now gotten in your heads at least a little better. So we have another paradigm that we're going to explore next, and this is the paradigm of simulation and a related paradigm of randomization. Now, this is quite enjoyable for me to talk about because this is part of my area of research. I do quite a lot of research into randomization, and in particular, how we generate random numbers for use in various different procedures. And random number generators, or RNGs, can surprisingly be used to solve problems that don't appear to have any inherent randomness to them. And let's look at one of those now. So we can see that by applying a fairly simple set of randomization techniques, simply by generating points uniformly at random within a specified range and calculating the ratio of points between those that fall within a smaller inscribed circle within that larger square area, we can actually compute the value of pi experimentally and empirically. Vincent?
If I remember correctly, isn't it that the only problem of this method is that it's not particularly efficient?
Yeah, this is not the most efficient way of calculating the value of pi. Probably the fastest way of calculating the value of pi is taking a circle and computing the ratio of the radius to the circumference. Well, that's assuming you know the power series. This is, let's say you don't know a priori what the value is. But yes, there are lots of different ways of calculating pi. This is more illustrating the surprising nature of randomization that allows us to solve a problem that doesn't seem random. The pi itself doesn't seem random. There's nothing random about it. It seems a fundamental part of the construction of the universe. But yet, by using a simulation technique, by generating all these points, we are actually surprisingly able to recover the value of pi. And that's more the takeaway here. This is not the most efficient method of calculation, but it's more illustrative of where this method might work. Operating systems also have ways to produce random numbers for us to use in programs like this. But at least in my area of research, I've been looking a lot at places where random number generators aren't working as they should, which might be fine for something like computing the value of pi if the error is very small. However, in computer security, random numbers that are generated by the computer but do not behave the way we would hope for random numbers to behave can actually result in very significant security vulnerabilities. And in fact, in my research, we were able to compromise thousands and thousands and thousands of websites on the internet because the computers on which they were running had bad random number generators. There are also a lot of significant and interesting algorithmic challenges in generating random numbers from a range. And if you want more of these, we've got a master's level class to tell you about that later. And one more round of applause for Annalise and a thank you. So we're going to take just 2 seconds and look at the version of Monte Carlo Pi on the laptop that I wrote, I think, last year. There we go. So we have a function that prints bits of whatever we want, but the interesting code is over here. So we are going to generate two 64-bit random integers, xp and yp, using the random function. And we see that this function is included in sys/random.h. And now I've done one interesting thing here, which is to call a function sRandom before I actually call the function random. What sRandom is going to do is something called seeding the random number generator. Now, one interesting property of computers is that at least the ones that we build are deterministic. So if you feed in the same input, you'll get the same output every time. So how do we get the computer to behave randomly? Well, the answer is that you mix in data that comes from a source outside the computer. So something along the lines of, what time did the computer turn on? Or when did you get a certain piece of information on the network? And you put in all those pieces of data into a function, and then the function behaves unpredictably because you don't know its initial conditions. And so when I call this function sRandom with the function time, this is saying mix in to this function the current time such that people can't then predict what the random numbers are. So if you get an old school calculator, a brand new one from the factory, and you get two people with the same calculator and you both hit the random button, it will actually print the same random number a lot of the time, because when you're hitting the random button, it's not being random, it's following a deterministic process, and because they're the same calculator, they might have been set the same way in the factory. So even though it looks random, it's not truly random. So we now have our process where we generate xp and yp, these two 64-bit random integers, and then we need to perform this slightly arcane-looking line of code in order to convert them into floating point numbers, so numbers with a decimal point that are distributed uniformly at random in the range 0 to 1. Don't worry about how we do this. You're not going to be tested on it. This is just showing you that it's not quite as straightforward as just tell the computer to generate a random floating point number. So that's what our code does over here, is we are relying on our knowledge of the construction of a float or a double here. In this case, these are going to be doubles, and using this knowledge in order to ensure that they actually are generated uniformly at random in that range. So now what we do is we count the number of points that we've generated that are within the bounds of the inscribed circle. So we have r here, which is the distance of our point from the center. So that would be if the point is at has a radius of 0.5, it's inside the circle with radius 1. And so we say if it's within inside that circle of radius 1, increase the count, and then just calculate the ratio of the number of points that fell inside the circle out of the number of total points. So let's give that a run quickly. Maybe we can leave that running for a bit, and it'll get closer as time goes. Okay. So there are two distinct features about this particular type of code, because there is a chance of getting an incorrect result with this particular type of method we're using. If you terminate the code too early, you'll get a result that doesn't converge on the correct answer, and this kind of procedure also doesn't have a clear termination point. How do we know when we're finished? Well, when we get the right answer. How do we know when we get the right answer? We don't. And so this is called a Monte Carlo simulation method. There is also another whole category of randomized algorithms called Las Vegas algorithms, and they always terminate with finite runtime. So there's some element of randomness, but at least you're guaranteed about a certain stopping point. Does anyone know why they're called Monte Carlo and Las Vegas? Vincent? But why those places? Tim? Yeah, gambling. So Monte Carlo and Las Vegas are places where there's lots of randomness, but that doesn't mean that there's not some expected outcome. So if you go to either of those places and engage in games of chance, chances are you will lose. In our simulation paradigm, one thing we could also do is use our numerical techniques to actually model a real problem and to try and get the behavior in an experimental or in a simulation method that might be a bit frustrating for us to work out analytically. So here's another example that some of you might have seen in your mathematics lectures. Here we have a load with a spring and some dampening and potentially gravity. And has anyone done this in Calc 2, I think it is? 2 weeks ago, yeah. So you might recall that this was a bit of an annoying problem to solve. It had lots of terms. You had to do a lot of hard work. Fortunately, we're not in Calculus 2 here. We are in Foundations of Algorithms. So we can write the whole thing down this way, everything we need to know. So let's write a formula for the acceleration, which includes the dampening of the spring, the dampening of the spring, the Hooke's constant of the spring, so how springy the spring is, the mass of the load, and don't have to worry about that. That comes from physics. So well, the physicists are getting grumpy at me for saying, don't worry about that. But essentially, this is more an example of if you're given a known set of rules about the behavior of a system, can you compute the future behavior of the system without necessarily having to be able to do the calculus that allows you to solve it analytically? So we take the formula for acceleration, which is going to be the main source of computations for this, and then we're going to take 3 approximations. So the change in the position of the spring relative to its starting position is the same thing at time t plus 1 as it was at time t0 plus the difference in time. So if it's been 1 second, that's 1, times the velocity of the spring. So if you know the spring is moving 1 centimeter away from you per second and it's been 1 second, then you can calculate its new position as 1 second further than it was before. Now, of course, in physics, we know that because there's acceleration, this formula isn't quite accurate because the velocity is actually changing all the time. But if we make the time step at which we look at this very, very small, the acceleration isn't going to have had much time yet to affect the velocity, and so this might actually be a reasonable approximation. But knowing that the velocity is going to be changing because of the acceleration, that's the definition of acceleration, is the amount that the velocity is changing, we can also approximate that. So the change in velocity is going to be the change in time that's happened multiplied by the acceleration. And to calculate, therefore, the new velocity, take the old velocity plus the change. Again, if we are looking at larger time steps, this is not going to be accurate, but it's going to be accurate for our small time steps. And then the last thing is we also have to update the time at every step. But our other three variables are going to change over time. And we can just simulate this using a loop where the core variable that's changing is the current time. So this is easier than a page of math. And even physicists who do solve these things analytically and properly also use this kind of thing too in all sorts of scenarios. So let's check this out in spring.c. So here I have a number of constants set. They're just from physics for a given setup. Don't worry about the graphing code. This is just going to be to print it nicely. What the core thing we care about here is this loop. And what this loop is doing is it's saying, okay, let's have all our variables set at the beginning just like we talked about. We have the current velocity, the current distance from the spring's original position, the acceleration, which is going to be fixed, the current time, the mass of the spring, and delta t is going to be the step size. So are we calculating this every 1 second that we're calculating the changes? Are we calculating the change every 0.1 of a second or 0.01 of a second? And this allows us to get more granular with our simulation. And as our time step gets smaller and smaller and smaller, our simulation is going to get more and more accurate because because the accuracy that we've thrown away by not properly updating the velocity, by not properly updating the position with respect to the change in velocity due to the acceleration, is going to be less and less of a large factor on a smaller and smaller time scale. So all we're doing here is until our spring has stopped moving, so we want to say if the velocity of the spring is, I think is this too large or too small? Yeah, so if the absolute value of our velocity, so it could be going either forward or backwards, if the velocity is smaller than some predetermined value, then the spring is now at rest. And so here we're just calculating our three variables, just like we had in our equations up there, and now we can give it a run. So it says the usage here, what is the starting position of the spring away from its original location? There we go. So let me start that one again. So this is starting the spring 1 unit away from the beginning. You can see that's where it started. It is a spring of weight 2 units, and we're calculating this in increments of 0.1. So it springs, and then it pulls it back a little, and then it swung pretty strongly to the other side, even more to the other side, and then it comes back, and you can actually see the spring here. So let's try it with a slightly different set of values. Let's start it off at 0.5. And so now it does a little less of the springing itself because there's a bit less energy there. So now let's decrease the mass and increase it back out to, what did I have it before? Let's decrease the mass. And now it's doing less of the springing because there's less pulling on it. And if we increase the mass, then we'll get this behavior there. And you can see it's doing a little more springing back and forth. Okay, what if we increase delta t? Our time step is now too small for us to actually see anything of value in the simulation. But if I were to choose something like if I chose a 0.5, what actually happened is the simulation didn't work very well and gave us a mechanical failure, even when in real life the system would have behaved better. So now if I set that to 0.01, we can see even with greater granularity what's happening. Tim?
I mean, that's kind of like the physical analog. If you were taking a video of the spring, right, and your frame rate was like 2 per second, it would just look really janky if you would actually look at the frames because you wouldn't be able to see the smooth movement.
Exactly.
It would just be like random intervals, and so you wouldn't be able to actually determine like what the frequency of oscillation.
Exactly. And so this simulation technique is very, very powerful, not just for solving physics problems, but you can use it to solve a whole variety of problems in different places in life as well. So one thing that I've included here in the slide pack for you is this interesting slide on simulating Monopoly to figure out what is the outcome, expected outcome for different players, and what should you do? Now, there have also been similar formal analyses of Monopoly to figure out what are the expected outcomes if you do this analytically. And watching this video, I found to be very, very interesting. So another type of algorithm that's next on our list to talk a little bit about is approximation. And so here the goal is to get as close as possible to the optimal solution or to a really good solution, even though we know that our method is not actually guaranteed to give us the correct result. And in some cases, we can know that it won't actually ever achieve the correct result, but we can hopefully bound the gap between the actual best solution, if we knew it, and the outcome that the algorithm would give us if we ran it. So one way of thinking about this is try and solve a slightly simpler problem that is tractable algorithmically, that approximates the original problem with some known or bounded error. And we do this all the time. So when I was talking about my workload allocation last week of trying to assign professors to classes, the algorithm to actually solve this optimally is quite tricky. So we can also run a version of that algorithm that just approximates the best assignment of people to classes given some constraints. And there are places where we really do this and where you'll probably encounter it at some point in your university careers. Examples are numerical integration. So if you have an integral where there's no integration method that we know of how to actually get the correct answer, that doesn't mean you're completely stuck. What you can do is break up the problem and try and approximate the true value of the integral, even if you can't get what we'd call the analytic solution. This is also true when we solve certain kinds of differential equations for which no known closed form solution exists. And this is very, very important in physics and chemistry, and indeed in the science that many members of your tutoring staff do in their jobs. I think probably Rithik over there likely uses some amount of approximation algorithms in some places in his work. A lot of places. And so the field of study that studies these particular types of problems is called numerical analysis. And it's, again, a very rich and deep field. But just to give you a small bit of a flavor of numerical analysis, we're going to look at the problem of approximating the cubed root of a number. Now, obviously, there are some ways that we can do this analytically for certain numbers. So for numbers that are perfect cubes, we can calculate their cubed root quite efficiently. But what about for an arbitrary number? So here we're just going to introduce a known result and then use that result to show you how you can implement that computationally and get an approximation algorithm. So this is called the Newton-Raphson method of approximation. We're going to spare you the full details of the method, but you can think of it this way. If you have q, which is approximately equal to 3 on the cubed root of x, so let's just say you have some guess. You don't know exactly what it is, but you know some value q that's roughly the cubed root. You can make a better guess than the one you already have. And the way you make a better guess is you take your previous guess and you plug it into this formula. So let's say 2 times your guess plus x, which is the number that you're trying to get the cube root of, on your guess squared divided by 3. That gives you a new guess that will be better than your prior guess. So we can just do this again and again. So take your better guess and get a better guess than your better guess. And take that new one and get a better guess than that. And keep repeating this process over and over and over until you've got pretty much as good as you're going to get using this process. And so when I say till we're not going to get any better, what we call this is convergence. When your answer is either converging to the correct value or it's not improving anymore. And so we actually have some code that shows us this process for doing this with cube roots. And so let's take a look at that. So at this point, hopefully you'd be able to write this code yourselves. It's not very complicated. Take in a value v, start with a guess of 1. It's a bad guess for the cube root of most numbers, but it's a guess, and as long as we can improve on that, we're okay. And then for a set of iterations, just progressively compute better guesses until you're done. So in this case, we're going to run this for a maximum of 25 iterations. And you can either try and detect when you're not getting better, or you could just do a fixed set of iterations. And experimentally, you can show that 25 guesses is pretty good for most real cases. So gcc croot.c-o. Anyone have a number that they're desperate to find the cube root of? So it spits out pretty quickly the cube root of 2. So it gives us this value, and then we check it again here when we're printing it out by actually performing the calculation. Now, another thing to note here is that we're also going to be subject to the problems associated with floating point numbers in C when we're doing this. So down below a certain size of number, this is not actually going to be accurate anymore because we're going to, in order to represent the cube root appropriately, we would need more decimal places than our floating point numbers can actually support. And so that's why we have the warning over here that the cube root might be inaccurate. So for these values, we don't think we're going to have enough space in our numbers to accurately represent them. Okay, this takes us to, I think, the last of our paradigms, which is optimization. And this is where much of machine learning and AI research falls into. So some of the time, even when they're not discussing it as optimization, that's really what's happening behind the scenes when we're doing machine learning. And the very, very basic formulation of this is, let's say you have some desired output y. Find me a function that when given inputs x, which are not all the information I could possibly need, but the best information that I can practically describe, find me a function f such that I'm best able to get y. Now, a real life example of this might be x is the text of a real estate listing, and y is the house, the actual value of the house. So not the listed value of the house on the website, but the price that it will actually sell for. Why would this be useful? Well, if you are browsing for housing on the internet and you want to buy a house, I know you've probably spent it all on avocado toast. So let's say that you are trying to buy a house and you want to find one that is undervalued. So put in the text of all the ads and you need to find the best function that gives you as close as possible to the actual value that the house will sell at. And that will enable you to find a house that is listed at much lower a price than it really should be. And so then you can make trades based on that. And so in the real world, we don't actually have all the data we want, and nor do we actually know ahead of time what the correct values for y are, because until the house is sold, you don't know actually the value that it's going to sell at. So let's try and imitate the real function f that we wanted to calculate with instead some other function, some model that is going to approximate that function f. And the better we can make our approximation function, our model, the better off we're going to do at predicting these outputs. A very common way of doing this, and probably the way that a lot of you that might have started sounding intuitive to you and that's talked a lot about in the media, is supervised learning. So this is where I will give you a whole bunch of examples of real estate ad, house the price sold for. Other real estate ad, what price the house sold for. And you do this over and over. And every time you get one of these pairs, you use the pair to adjust which function you've picked. And when I say adjust which function you picked, imagine you just have a linear regression. A linear regression, y equals mx plus c. Choose the right m and the right c to describe the data. That's the simplest version. And every time I give you another point on your plot, update your guess for the m and the c. Now, of course, in real-world machine learning, most of the time we're not doing linear regressions, at least not simple linear regressions like that. The functions look much more complicated, and instead of just having m and c, we might have tens of parameters, we might have thousands of parameters, or in the case of large learning models, we might have billions of parameters. And that's actually what's happening in a large language model, is the same fundamental idea as a linear regression. You have a whole bunch of points and a whole bunch of outputs you want to get from each of those points in your graph somewhere. And the goal is to pick the right parameters such that the function you have generated does the best job of matching your input points to the output points from the pre-existing sample. Now, of course, that's a oversimplified way of talking about large language models. So sometime I'm more than happy to chat to you about how this actually works a little more under the hood. There is also a second paradigm called unsupervised learning, which is attempting to do something perhaps like clustering data together such that the clusters make sense. So can you tweak your output to make the model better and better, even if you don't actually know ahead of time combinations of correct input and correct prediction? And one way that this is generally done is by taking your model, putting an input pair through it, seeing what it predicts, and then checking how far away the prediction is from what you wanted it to do. And then based on the direction that you have to tweak things in order to make the outcome a little closer to the true outcome, you change the parameters. And this is called gradient descent. And this is probably something that will show up over and over again in your academic careers. So with that, we've actually covered a lot of the major paradigms of design of algorithms. Well, maybe you don't need to do DOA anymore. I would probably recommend still taking it. You're not quite ready yet. So now we can think of categorizing our algorithms a different way rather than just the paradigms. And this is going to be calling back to Dick Karp's discoveries and contributions to complexity theory, which is the study of the classification of algorithms into how hard they are to solve. Now, I've already done some of this. We have some very basic categories like big O. So we can say like big O over n squared is all functions for whose worst case runtime is less than n squared multiplied by some constant. We can go back to the formal definition. And there are a bunch of different ways that you can classify algorithms based on their complexity, because we might want to classify algorithms that are deterministic, different from non-deterministic, different to ones that run on a quantum computer. And so the next chunk of our lecture is going to talk a bit about these classifications and what they tell us about the universe itself. Now let's hear from Gav, who's got a question. Oh, sorry, honey. It should be on. No?
Oh, hello. So we were talking about the supervised versus unsupervised learning. The example of gradient descent, that would be supervised, correct? So how would you, if you had unsupervised learning, how are you going towards a goal if you don't know what the goal is?
So you still need to have a goal, but the goal is then not going to be provided by your input data, by your training data.
Okay.
So the goal might be, for example, let's say you have some similarity metric between different points. You want points to be maximally far apart if they are dissimilar and maximally close together if they are similar.
Yeah. So it's still something you can measure in some way. You just don't know what the final state is going to be. Okay, nice.
Ron, did you?
other thought is hostile neural networks. Another example. If you've got, say, a game of Tetris, you just have like tons of simulations running different random inputs, and when it gets the best score, you basically treat that as the closest to the true solution.
Yeah, that's a really nice example. I might use that next year, actually. It's a nice one. Okay, any more on that before we go to complexity theory, which is kind of the pinnacle of computer science in a way. So it's very exciting. Okay, so to take us into our discussion of complexity theory, let's go back to Sudoku from last week. So if you remember, it's this grid of squares, and you have to fill in the squares from 1 to 9, and we had this kind of interesting discussion about formulating it as a constraint satisfaction problem where we had like a million variables and relationships between the variables, and then we tried to get some program to actually figure out how to satisfy all the variables in a way such that we didn't break any of the rules of the Sudoku. So if you remember, we had some starting assignments for our variables. So we said like, okay, the 9 is in square 0, 0, so the variable 0, 0, 9 should be set to 1. And then we had a whole bunch of different clauses that set up the rules for our Sudoku. And so we ended up with, I think it was 10,000 clauses that defined the Sudoku. So our question at the end of this was, is there at least one setting for all the variables such that we don't break any of the rules? And if there is such a setting, can you tell us what it is? Now notice there's a slight distinction between those two kinds of questions of, is there a setting for this? Is there a setting of the variables such that the Sudoku can be solved? And what is that particular setting? So it's the distinction between asking, is there a valid solution to this problem, and actually being able to provide the solution. And in today's lecture, I am probably going to gloss over that distinction pretty considerably, even though it is fundamentally important in theoretical computer science. So for most of today, we are going to be talking about just the decision problem of answering, is there a valid solution to this problem that I presented, rather than give me the specific one. We can talk more about that offline. But this general problem of trying to find a set of settings for the variables that don't break any of the rules is called satisfiability, and we mentioned this very briefly last week. Now, of course, there was this paper on how to convert any Sudoku into one of these problems, and we did, in fact, demonstrate it ourselves. So this is where things start to get interesting. So if I give you a collection of variables, how long till you know if you have a valid solution to the Sudoku? So if I give you all the values for S, X, Y, Z, how long till you know if the potential solution that I've given you is in fact a correct solution or not?
I guess you would have to check if the first constraint is valid and then the next constraint, and you'd have to do that to see if they all are. So in the worst case, that's probably like O of n.
Where n is
the amount of constraints.
The number of constraints. So this gives us a solution to the problem in terms of the number of constraints. And we can also bound the length of the constraints pretty effectively for this. We know that the constraints are of a constant size. So the longest constraint is going to be the combination of the conflict between one row, say one column and two other rows. So you check one column and you check that no row violates it. So that gives us information that essentially we can parameterize this in O of the number of constraints that we have multiplied by some fixed maximum length of the constraints, which is still going to be O of the number of constraints because that number will be a constant. Another way of writing this is O of n, where n is the length of the string made up of all the constraints. So if you wrote out all the constraints in a row, we could know just by checking character by character by character by character if those constraints were satisfied. And this is also big O of n to the power of k. Why? Well, if it's big O of n, it's also big O of n to the k because n to the k is bigger than O to the n. And remember, big O says that it's at least smaller than this. So you can always pick a bigger big O, and if it's bigger than your original one, you're still okay. And this is what we call polynomial time. It means there is some polynomial that we are big O of. It doesn't matter whether it's O squared or O to the 3 or O to the 500. This problem's satisfiability can be checked in O of n to the k. So what we're going to do as a result is we're going to say that satisfiability, the decision problem for satisfiability, so is this solution correct or not, is going to be able to be done in big O of n to the k, which means it's doable in polynomial time. So we're going to create a new category of problems. All problems for which, if you have a solution, you can check, or a potential solution, you can check if that solution is in fact a correct solution in polynomial time. So is the procedure for checking if your solution is correct big O of n to the k? And we call this class of problems NP. Now, who has heard of NP in the context of computer science before? A couple of hands go up. Okay, so this is where you actually get to start to understand what it is. And NP is the class of all problems that can be checked in polynomial time. Or really, I should say all classes of problems, or all categories of problems. So it's not that this specific satisfiability instance is solvable, has a checkable solution quickly. It's that all satisfiability problems, no matter what satisfiability problem you have, is checkable in polynomial time. And this is true not just of the Sudoku version, but of any satisfiability problem. And so what we can say, because we have a way to convert any Sudoku into a SAT problem, we're going to say that Sudoku reduces to SAT. What this means in other language is if we have a way to tell whether a given SAT problem, whether any given SAT problem has a valid solution or not, then we can also do that for any Sudoku. If we can do that for every single SAT that someone gives you, then if someone gives you a Sudoku, well, you say, I know how to check if that Sudoku has a valid solution. My step is first convert the Sudoku into a SAT, and then check if the SAT can be solved. So that's what we mean when we say a reduction. Sudoku, checking a Sudoku, can't be any harder in terms of complexity than checking a SAT. Because anytime you give me a Sudoku, I can always make it into a SAT. So if I can solve all the SATs, then I can solve the Sudokus. Practically, we can actually solve a Sudoku on a laptop, but generally that's only because n is small. The actual size of the Sudoku is small. If instead of like a 9 by 9 grid, you made the grid much bigger, the computational cost would quickly blow up. So the ability to practically solve a problem does not actually tell you whether that type of problem is fundamentally hard or easy. That has to be done independently, because if a problem is small, you can even just solve it brute force yourself. You know you can solve a small Sudoku. That doesn't actually tell us much about the nature of Sudoku itself. And just a side note that might be important is we can also show that for any SAT, no matter how many clauses it has, there's always a way to break it down into a version of SAT such that you only have 3 clauses at a time. So you have this set of 3 clauses, and that set of 3 clauses, and that set of 3 clauses, and that set of 3 clauses, all of which must be true. So there's just a way to break the problem down. So this is reducing Sudoku to SAT. What about other problems? Are there other problems that also have this nature where if you can solve this one type of thing, then you can solve this other type of thing? So here is a fun one for you. Ethan, can you color the states with 2 colors such that no states with the same colors touch?
Just by looking at it, I'm going to say no.
Okay, can you explain why?
My logic is that Queensland is touching 3 states.
Yep.
And since we only have 2 colours, pigeonhole principle kind of kicks in, and we can't give 3 states only 2 colours without replication.
Pastor Vincent as well, who has a comment.
But the Northern Territory is not a state.
Fair point, not the point.
You don't have to bother.
So here we have a representation of the map where I've tried to color it. So this is a verb that we use in computer science to color something or to 3 color something. In this case, I've tried to color the map of Australia, and you can see that at least for South Australia here, if I chose an orange, it would conflict with Western Australia and Victoria. If I chose a purple, it'll conflict with the not state of the Northern Territory. So there is no way to two-color a map of Australia, and you can convince yourself this fairly easily by trying every possible combination or by coming up with this logical impossibility. So, nope. So let's pass the microphone along. Who's behind you, Ethan? Yeah. Okay, so here's the next problem. Can you color the states instead of 2 colors with 3 colors with the same rule? So I'll show you the 2-color map. If I give you a 3rd color, can you 3-color the map of Australia? So explain what you would do. If I gave you a 3rd color?
Actually, I don't know the state. Just put another color.
In which one? You can... South Australia, yeah. So if we put our 3rd color in South Australia, then we actually will have a successful 3-coloring of the map. So there we have our beautiful, accurate map of Australia. So here's the question for you, Daniel. Is this problem in NP? If I give you a solution, can you check in polynomial time, so in big O of n to the k, if the solution that I've given you is correct? So why no?
Because the map can get and size can be very large.
It can be large, but I'm saying as it gets larger, I'm also giving you more time. So if I add 1 state, how many extra checks do I have to make? Let's say I put a state over here. Would I have to make any extra checks? Okay, if I put a state in the middle of Western Australia, would I have to make any extra checks?
One check.
Okay, 1 check. What is the maximum number of checks that I would have to make?
All existing points.
If I add another state, in the worst case, I would have to check it against all the states that it touches, and we could imagine a world in which the new state touches every other state, although we'd get an answer pretty quickly there. If it's touching all the other states, then we know that it's not possible to 3-color it. And so this problem is actually going to be in NP, because we know that if we are bounding it to each state to have a maximum number of neighbors, if we are bounding each state to have a maximum of n neighbors, then at worst case, we're going to get n squared. So let's instead represent this map as another map of Australia. This still look like Australia? Right, we have a graph of Australia. So what is that over there? That is Tasmania. So this is just as good a representation of the map of Australia for the purposes of 3-coloring. So the way we would check if the map has a successful, if this coloring is a successful 3-coloring, is for every vertex, check if its neighbors are of different colors. If at some point you reach a node, and from that node it has a neighbor that's the same color, then you know that the solution is incorrect, because that would be 2 states that are next to each other that have the same color. Vincent?
I guess there's you just implement to solve if what's the scale you are optically per.
Yeah, similar kinds of things, and we'll talk about that in this class, perhaps. Anyway, so it turns out that 3-coloring is reducible to, that map coloring is reducible to this kind of graph problem. In fact, this is actually the canonical representation of 3-coloring. So we can check the solution by examining each vertex's neighbors. Each vertex can have a maximum of n neighbors, which gives us a big O of n squared, which is still polynomial time, which means that graph 3-coloring belongs to NP. But can we turn it into a SAT problem? So let's say that we have solutions for how to solve a SAT. Would this mean that we also have a solution for how to solve 3-coloring? Seems like an interesting kind of problem. So just like we did with the Sudoku where we had a whole ton of variables, let's convert our graph into a whole ton of variables. So we're going to have 1 variable for each node being colored a specific way. So let's say we have 3 variables for node 0, and I think node 0 might be Western Australia by memory. So let's say we have 3 variables for the state of Western Australia. If Western Australia is orange, then it will be, I forget which color is which in terms of my rules. Doesn't really matter. So let's say that 0 is orange, 1 is purple, 2 is green. So S00 is node 0 orange? Is node 0 orange in this case? Yes, so that's set to 1. Is S01 true? So is node 0 purple? No. Is node 0 green? No. And so this clause says that node 0 must be at least one of the colors because one of these 3 things must be true. In this case, we have successfully satisfied this constraint because 0, 0 is true. But note that this clause doesn't say that only one must be true. This clause itself only says it must be at least one. So we'll need another clause to stop it from having 2 colors. We can also write this other clause to say that the node can't conflict with its neighbors. So in this case, node 0 is connected to nodes 1 and 2. And let's read this out a little bit. So this says, assuming that node 0 is orange, then it must also be the case, that node 1 is not 0 and node 2 is not 0. And what I mean by 0 is orange. So this says, if node 0 is orange, then it must also be the case that neither node 1 or node 2 are orange. So that's part of what we want. But we also want it to be the case that if node 0 is purple, then neither of its neighbors are purple. And we also want it to be the case that if it's green, that neither of its adjoining nodes are green. And using this, we can actually write out the whole problem this way, by encoding the relationships between all the graphs into a lot of clauses. Now you might ask, why do we do this? Why would I bother converting the graph formulation, which seems far less complicated, into the satisfiability problem? And this is because it allows us to obtain the following result. If we can solve all SAT problems in polynomial time, then we could also definitely solve any map 3 coloring in polynomial time. Garb, how do we do that?
By reducing it to a subproblem.
So explain that in easier words. Do we have a microphone? Honey's got one.
By trying to represent the map 3 coloring problem as a set of Boolean conditions, which ends
So
up being
step 1, I give you a map. What do you do to the map?
try to represent it as a graph.
Okay, I've given you the graph. What do you do?
Try to formulate some constraints that will allow me to represent how I want the final
And
condition.
then what do you do?
And then I go through every node and try to make it satisfy those constraints.
Well, this is just assuming that I've given you a magic algorithm to solve SAT problems.
Oh, so I verify if those nodes do satisfy those constraints.
So
And-
I've given you a magic algorithm that can solve any SAT problem. You use your magic algorithm, and now you have the values of the variables, and then you just go backwards. You say, okay, from my variables, I now know I can convert those back into what they represented for the graph 3 coloring, and then for the graph 3 coloring, I can convert that back into the map. Problem solved.
Yep.
And what this means is that at the end of the day, graph 3 coloring can't be harder than SAT, because if it was harder than SAT, then it doesn't make sense that we could have a magic algorithm for SAT that would also solve all the graph 3 colorings. So it must be the case that because we can show this reduction, that graph 3 coloring can't be harder than SAT. And so what this is called is if we can show that all instances of one problem can be represented as another problem, another class of problem, we're going to call this the reduction. There is a caveat here, and this is a very important caveat, which is that the conversion process must also take no more than polynomial time. The reason is if it took more than polynomial time, then you'd actually be cheating by doing extra work in that conversion step. So if your conversion step was solve the problem and then write it out in the other format, you haven't actually used that other format to solve it. You've just hidden things in your conversion process. And one kind of other fascinating thing that we can show is that Sudoku is really just a fancy version of graph coloring. So if you imagine that instead of 3 colors, we have 9 colors, then all the squares on a row are connected to each other, and all of them must have a different color, which is the same thing as saying they must all have a different value. In this case, being a different color and being a different number are equivalent. So let's do one more proof, and this is for subset sum, and show that subset sum is NP complete. And we'll talk a bit more about this in a minute, what it means to be NP complete and not just NP. So, is subset sum in NP? If I give you the items that total to a given target to fill up the backpack, can you quickly check if those numbers do actually add up to your target? And Garb, do you want to pass back to Lottie maybe? Lottie, you awake enough?
We'll have to find out. So what I'm thinking here is that it's very easy. Are we answering the question on the board?
It's
very easy to check the sum of any subset, right?
Yeah.
If you have a list of numbers, you just add them up. That
add
takes
them up, and
linear
then
time.
if they add up to your
And then you
target,
just check yes or no, which takes constant time. Yes or no, is our sum the same?
so this is definitely checkable in the length of the string, where the length of the string contains the weights of the items. So if the string is like item 1 is 100 kilos, item 2 is 250, item 3 is 350, does that add up exactly to 500? You can just go along each of those binary digits, let's say we've written out in binary, and check very quickly just by one run through and doing the addition if you do indeed have a correct solution. And so this is our algorithm to check the solution, which is just sum everything up. We can, and because we can check a solution in O of n to the k time, that means that subset sum is in NP. It's an NP problem. Now, our other question is, can we now reduce subset sum to a problem that we know is in this other category called NP hard? And NP hard is going to be this category of what we think are all the hardest problems in NP. And the hardest problems to find a solution for, not to check the solution for. Again, this is different from checking a solution if someone gives it to you. This is about finding the solution. So we've seen that SAT was very easy to check, but it seemed to be hard to find a solution. Same thing with graph coloring. Graph coloring was easy to check, but seemed a bit harder to actually find the valid solution. And so can we find a reduction as well for subset sum so that we can reduce subset sum to one of these problems that we believe are hard? So if we can show that we can solve every 3-sat problem using subset sum, that means that subset sum must be at least as hard. Because if we know that 3-sat is hard, and we can turn any 3-sat into subset sum, 3-sat is just sat with 3 clauses. So let me repeat that once more slowly. Let's say I tell you for sure that 3-sat is hard, that we don't believe that there is any algorithm that we could use to solve it quickly and efficiently. Say no polynomial time algorithm exists. Whatever that is, if we can take any 3-sat problem and convert it into subset sum, and I've already told you that we know for sure that 3-sat is hard, that means that solving subset sum must be hard as well. Because if it wasn't hard, then that would mean that 3-sat wasn't hard, and that's a contradiction. I've told you that 3-sat is hard. Garv.
Thank you. How do we know that SAT is NP hard though?
We don't know that it's hard yet. I'm just telling you for the minute. Let's assume that it's in this category of hard problems. Okay. Then we'll do this magic master stroke and I'll wave it away. But for the moment, just trust me. We're going to say subset sum we believe is in this category of hard problems.
Yeah.
And there will be reasons for that, which we will disclose. But it turns out there's an open question there as well.
Yeah.
Okay, so if we believe that that 3-sat is hard, and we can convert any 3-sat into subset sum, that means that subset sum must be hard as well. Because otherwise we'd have a contradiction, because I just told you that 3-sat was hard, and if subset sum is easy, that would make every 3-sat easy. But I told you it's hard, so that's a contradiction. Okay, so now let's do the actual reduction, which shows that I can convert any 3-sat into subset sum. Now this is the hardest reduction I'm going to show you in the class. Normally you only do reductions in 3rd year CS anyway, so this is already like well beyond the material for foundations of algorithms. So here I've made up a grid. And on the right side, I have my 3-sat. So my 3-sat here says that, this is another notation, says that it must be the case that only that one of y, z, or not x are true. So at least one of those variables must be set to 1. So not x is set to 1 if x is set to 0. Likewise, if y is set to 1, not y is set to 0. So I have my 3 clauses. It must be the case that not x, y, or z. Clause 2, x or not y or not z. Clause 3, not x or not y or z. This is just a standard one of these kinds of satisfiability problems that we've already seen. Choose some combination of setting x to true or not true, a combination of setting y to true or not true, and a combination of z to true or not true, such that all 3 of these are satisfied simultaneously. So let's write it out in this kind of funny table form. We see that in clause 2, x is set to true. So in x's row, set the value 1 for clause 2. For not x, that appears in clause 1, so set its value in clause 1 to be true. For y, so put a y in the ones column because we're dealing with y now, and then for clause 1, set y to be true, and for clause 2 and 3, set not y to be true. And I haven't told you how we came up with this construction in the first place. This is the art of building a reduction from first principles, which is a research task. There's no known method to automatically come up with these. This is a result that someone famously discovered once upon a time by thinking really hard about the problem and by understanding all the tricks that one can generally use to come up with other reductions. Okay, we do the same thing for Z, and then we have these funny ones for W. And the W here is just going to be to allow us to ensure that at least one of these values, that at least x or not x is picked, and that at least y or not y is picked. You can't just ignore those variables. And at the end of the day, what we're going to try and do is we're going to try and force the rule via subset sum that our numbers are going to add up to what's at the bottom in our column there. So we're going to add these columns up to 4, which is the number 4 comes from 3 clauses in the SAT plus 1, and we'll see that in a second. And for every variable, we should have only one of their settings allowed. Either they're true or they're not true. And so you can see if we chose both x and not x to be true, this column would have summed up to 2, and that's not allowed. So that column is going to enforce for us that only x or not x can be true. You can't have them both true at the same time. So this is how the reduction actually works. Choose choose either x or not x, and that gives you one of those 2 numbers. So 100010 or 100101. Choose one of those. Tim, is there an error?
Each of these letters, X, Y, Z, X or not X, Y or not Y, and there was a 1011, whatever. This represents each node in the graph and whether it is colored color represented by X.
So we're not doing a reduction from graph coloring at the moment, but it's the same sort of thing.
So it could represent something like that. Okay.
These are just variables in our satisfiability problem. And I'm showing that for a given satisfiability problem, you can convert it this way. And so X, Y, and Z are just some variables in your satisfiability. It could be, like I said in the other one, we could have like X00, X01, but those are equivalent to like X, Y, and Z. So in this case, for what we're going to ask our problem to do is choose one of X or not X, choose one of y or not y, choose one of z or not z, and then finish off with one of these W lines that we've added at the bottom there. And so the task is going to be choose a selection from these items such that when you add them up, you get this specific number. And you have to get exactly that target amount. And all of a sudden, this looks exactly the same as subset sum. We have taken a collection of variables and their settings and figured out how to turn them into strings of numbers such that the only way to successfully get the target is if you have also satisfied all the clauses, which is kind of magical. It takes me a while to get my head around this every time that I present this. So I'm not expecting you to deeply intuit the understanding of this just off the top of your head. You actually have to go down and write the numbers out yourself and see, oh yeah, the only way that I can possibly choose the numbers to hit the target is if I also simultaneously are choosing a valid set of variables to satisfy the satisfiability problem. And this is crazy, crazy cool. We have just turned problems that seem like totally different, this satisfiability thing, into a much more numerical problem. And so what was going on here, just to remind you, is the first three of these, having this setting, if you look at the way they're set up, if I choose x and not x and I add them together, then I will get a 2 in that first place there, which means there's no possible way to satisfy subset sum if I've chosen both of these. Likewise, in the second place, let's say if I choose y and not y simultaneously, then there's no way for me to get that 1 in the second place in that column. And you can do this for each of the clauses and for each of the variable settings and see that it actually works. Super cool. So this is where it gets a little bit more mind-blowing. It turns out that a lot of problems in computer science are deeply related in this way, including the Eulerian bridges that Vincent was discussing earlier. That's an example of another type of problem which you can look up. I think that's the Hamiltonian cycle problem is what that turns into. And so you can actually produce this beautiful chart of reductions that shows which problems you can reduce to which other problems. And it turns out that we can get all the way to satisfiability over here. So we can show that all of these problems are reducible to SAT, which means that if SAT is hard, then these problems are hard as well. And there are also, along with a unidirectional reductions, we can also do the reverse proofs. So you can show from any given graph, any given SAT problem, you can turn it into a subset sum, and you can turn any subset sum into a SAT problem, which means they're equivalently as hard as each other. And what ends up happening is we end up being able to prove that if you can solve the hardest of these problems in polynomial time, then you can solve them all in polynomial time. If we can show both that the problem can be checked really quickly, but also that if we could solve it, then we could solve all the other hard problems, we're going to call this NP complete. It's both an NP problem, it's NP hard because it's an NP problem that is one of these really hard ones, and those two things combined create something that we call NP complete. So an easier way of saying it is that it is easy to check, but hard to solve. Now, I think it was Gav asked the question of, do we actually know that these are hard? So we saw that we had this beautiful, beautiful major, probably the crowning theoretical result of computer science in the 20th century was the Cook-Levin theorem, which essentially showed that if SAT is solvable in polynomial time, then all problems in NP can also be solved in polynomial time. So essentially, you can take any problem that can be checked quickly and solve it quickly as well, if SAT can be solved quickly. And this gives us a really good reason to suspect that SAT can't be solved quickly, because this would mean that any problem that you can check fast can also be solved super fast. And that would have significant ramifications. And we'll talk about that for the next couple of minutes. So here again is our picture. NP hard is the category of all the problems that are as hard as the hardest problems in NP. So it includes some problems that aren't in NP themselves, but are as hard as the hard problems in NP. NP complete is the problems that are both in NP and are also hard, NP hard. But now we finally get us to Garv's question. Is SAT solvable in polynomial time? And this is probably the most famous single question in computer science. Does anyone know what it's called? Does P equal NP? Is it the case that every quickly checkable problem has also an algorithm to make it quickly solvable? And these are the two versions of the world. If we live in the world where, let me say that a bit more slowly. P is the set of all problems for which there is an algorithm that will solve it in polynomial time, that will solve it in O of n to the k. So this is our world over here, where P equals NP. They are the same set of problems. If you can solve a problem quickly, it's in the same class as if you can check a problem quickly, it's in the same class of problems that can be solved quickly. So that still means there might be some hard problems out in the world, but those might be problems that don't have a quickly checkable proof. Tim.
So an implication of that would be, because we know Sudoku can be checked in polynomial time because it's NP, although you said the best known algorithm is exponential, if that were the case, it would imply that there is an undiscovered algorithm which can solve Sudoku as fast as, well, maybe not as fast, but at least in polynomial time.
Exactly. And if we could solve Sudoku quickly, that's the same as being able to solve SAT quickly. And if we can solve SAT quickly, then we can solve all the problems in P quickly, which would mean that we're living in this world, which would be really weird for a whole bunch of reasons. This is the other version. This is the one where at least most theoretical computer scientists think we live in this world, where there are some problems that are easy to check and also easy to solve. There are some problems that are easy to check and hard to solve, and there are some problems that are both hard to check and hard to solve. Let's give a microphone to Danny.
You said that if we found a way to solve Sudoku quickly, then it would mean that we had to live in that world.
Yeah.
Does that mean that since Sudoku can be reduced to SAT, does that mean all SAT problems can be reduced to a Sudoku?
Yeah, you can do the reverse reduction as well. Yeah, so if you are really, really, really good at Sudoku, there is $1 million waiting for you if you can show that you're actually able to compute them in polynomial time. Unfortunately, we don't believe that such an algorithm exists. And most people who try to answer the question of do we live in P equals NP or P does not equal NP are cranks. And there is this fun website which lists all the people who have tried, and these papers are generally garbage and would not recommend reading. And this gets to some really deep parts of computer science. Given a mathematical theorem written in a certain formulation, it can be easy to check if the theorem is correct. However, is it also possible to generate all correct theorems efficiently? I don't know. If we live in the world where P equals NP, math becomes easy because we could just have an algorithm that comes up with mathematical proofs for us. There are a whole bunch of real-world problems as well that fall into, and that would be solved if P equals NP. So cryptography would fall apart. Cryptography has some interesting properties in more subtle complexity classes that we're not going to talk about. But you could steal Bitcoin if P equaled NP. Bitcoin wouldn't be secure. You could calculate the best route for Ubers without much effort. You could solve the backpacking, scheduling, speech recognition. Lots and lots of real problems in the world would be automatically solved, or not automatically solved. We would show that they're not, in theory, hard to solve if we lived in the world where P equals NP. Now, the problem is some of these you might say, well, we do these things. We do like speech recognition, we do cryptography, we do scheduling. What's the deal? So we do solve Sudoku, and what's happening is in practice, we can generally solve particular instances of these problems, and there are often approximation algorithms that get us pretty good. But this whole discussion about complexity classes is for all instances of the problem. And so this generalizes the problem in a much larger and more complete way. Tim, was that another question?
I guess I was going to ask, polynomial time, we say, oh, if cracking Bitcoin cryptography or whatever was possible in polynomial time, then it would be the end of encryption or whatever. But what if it was just like an obscenely high polynomial? Like, what's stopping that from being like n to the Google? Nothing. So it could be that, in theory, it could be that p equals np, and we're safe because it's like an obscene.
So that would be a very sad world where we can prove so there are two versions of this. We can prove that there exists algorithms for these things, but we have no way to discover those algorithms. In which case, we're kind of a bit sad in one way. And the other sad way is we discover the algorithms, but in practice, they have such large constants or such large powers that they can't actually be implemented in the real world. And that would also be sad in another way. But one thing you might have noticed just in this class is that most of the algorithms that we've looked at actually tend to have pretty small powers on the polynomial, like n squared, sometimes n cubed. So we'd be pretty surprised to discover new algorithms that were kind of super important, that had really, really large powers. But there seems to be something like kind of interesting going on here that's a little bit more about under the surface, because suddenly we're talking about what would this weird computer science result mean for a whole bunch of what seem like super, super fundamental problems to the structure of the universe, a little more than just computers. And this is why I think theoretical computer science is actually super interesting, is because it does speak to actually a lot more than just computer science. I think, in my understanding at least, physics and the laws of the way things work, economics, are all very deeply tied to computer science, and computer science is a tool that we can actually use to understand how these parts of the universe work. And in fact, this is one of my favorite computer scientists, Scott Aaronson. We've seen when we had the black hole discussion earlier in semester, we used one of his papers as well. But he has this beautiful paper, which is readable by all of you, called NP Complete Problems and Physical Reality, which essentially asks the question, so what would it mean for the universe if P equaled NP? So if P equals NP, the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. And if you let that sink in for a minute, that seems pretty deep, and the rest of the paper is filled with insights like that. And so that takes us to the end of our very brief tour of theoretical computer science. The good news is none of that is assessed, even though whatsoever. It's not assessed at all. In third-year computer science, you might touch some of it. But in my mind, it's actually one of the reasons to study computer science. I think this is legitimately kind of beautiful and kind of fascinating. And even if you didn't follow the details, and I certainly, when I prepared this for the first time, didn't follow all the details. I have to keep going back over it. And the directionality of reductions is tricky, it's hard. But putting in the work here really gives you a feeling of connectedness to the universe that I think is kind of special and powerful. And so I hope that that's one of the things that you take away from this class is, okay, the big O proofs, they're hard, sometimes they're kind of useful. I can see how they'd be used in engineering. But you've actually started learning something that's much deeper than about you and your career. This is touching on something that seems to be of fundamental importance to the way stuff works. So this could be, for example, this could be, in my view, one of the religious moments in computer science, where we seem to be touching on something closer to the heart of reality. So when a lot of people have existential times as a teenager, asking, does God exist? Why am I here? How is the universe constructed? What does this all mean? And I think this is legitimately a place where computer science touches on some of those realms. And so I hope that through this chunk of the lecture, you've had a chance for it to touch you in that way, in the same way that it touches me. So maybe this is the end of Foundations of Algorithms, but I want to give you a career takeaway that you can use as well after all of this kind of heady stuff. So we'll do one more problem, one last problem for the class. So let's go back to calculating the nth Fibonacci number. If you remember all the way back in semester, we're going to take one last look at it, and through the lens of a bunch of the stuff that we've done before. When I was doing programming interviews for internships, this was the problem that came up the most frequently, just as a quick tester. But I'm going to give you the skills now to absolutely kick it out of the park.
A human X chromosome contains hundreds of genes associated with a wide range of diseases, including hemophilia and red-green color blindness. An interesting aspect of the X chromosome is its inheritance pattern. Unlike the Y chromosome, where the number of possible ancestors must be equal to the number of generations, or the 22 other autosomes, where the maximum number of possible ancestors is equal to 2 to the power of the number of generations, X chromosome inheritance is a little more complicated. A male will inherit one of 2 possible X chromosomes from his mother, either from his maternal grandmother or his maternal grandfather. A female will also inherit one X chromosome from her father, introducing an asymmetry in the number of possible ancestors. Turns out there's an efficient way to calculate the number of possible X chromosome ancestors using the Fibonacci sequence. For a male, the number of possible ancestors is equal to the nth Fibonacci number, where n is equal to the number of generations going back. For females, this method can also be used, but n is equal to the number of generations plus 1.
So that is one of my closest friends, Michael, trying to justify to you why it's actually worth spending more time on Fibonacci. But other than that, this puzzle is also used as a screener in interviews to check whether you've got basic programming capabilities. So who wants to give me the first go at writing an algorithm that can compute the nth Fibonacci number? Come on, someone's happy to do it.
I'm the same.
Okay, we'll give it to Darcy. We've heard from Danny once today. Sorry. Danny, maybe we'll pick on you in a minute. Okay, new file. Let's call this Darcy Fib, and I will put it up on screen. Okay, hit me. Just write the function. Let's ignore the header and the main function for the minute.
You would just start with your function, which would return an integer.
Tell me what to type.
Int Fibonacci. And then int n and
seems as good as every other letter.
and then int m as well.
Why do we want int m?
Because you would, well, hang on, I'm trying to do it recursively. Yeah, no, it's just int n for now, and then you'd need another function for the recursion.
And you know what? Let's make these longs instead of ints so that we can represent bigger numbers.
Yeah.
Okay, keep going. We've only got like another 15 minutes in class, so you got to be chop chop.
And then create another function which also returns a long, which is Fibonacci recursion. And that will take 2 more longs, call them, I don't know, n and m. And then return wait, hang on.
Danny, do you want to help him out?
I don't think you need the second function. The first function return, well, okay. If n is less than or equal to like 1, then return 1.
Yep.
Otherwise, we're going to do return fib of n minus 1 plus fib of n minus 2.
So remember, the nth Fibonacci number is just the sum of the nth minus 1 and the nth minus 2th Fibonacci numbers. So this is our basic structure. In fact, I've written it out for us over here. This is the simplest version of the Fibonacci calculation of calculating the nth Fibonacci number. You should all be able to do that for programming interviews pretty quickly. So Darcy, get cracking on practicing that one. And in fact, here I've done longs to allow us to do it with even bigger numbers. So let's try this out.
How many longs can you have?
Just long, I think. No comment. CD. Fibonacci 12. Fib 1. Let's calculate the 7th Fibonacci number, and we get our normal recursive thing. I get 21. You can just see each time I'm printing out which Fibonacci number it's printing out. So like the nth Fibonacci number, am I printing out the, am I calculating the 7th or the 6th or the 5th or the 4th, etc., etc. So very simple program. So implementation 1, I'm just giving you the big O runtime here. It's recursive at 1.7 to the n, which is not that great, but it's easy to code, so we get some win there. Okay, how can we improve on that? Danny, you've still got the microphone.
Well, you could do it.
Iteratively.
So we could do it iteratively. Is there a way for us to improve the recursive one? So every time I calculate, like let's say I'm calculating the 4th Fibonacci number, that means I need to calculate the 3rd Fibonacci number and the 2nd one. So let's say I'm on the recursive side where I'm calculating the 3rd. The 3rd is going to compute the 2nd and the 1st. And the 2nd Fibonacci number is also going to compute the 2nd and the 1st. So what do we have going on?
You call the same function with the same inputs more than once?
Yeah, I'm doing work repeated times. So when I have repeated work, what's normally a better way to deal with that? If you're doing the exact same thing multiple times, should you recompute the value both times?
No, you should like store it in like a cache. Or...
Yeah, we can store it. And this is a process called memoization. So if you are going to reuse the same value for a function multiple times, what you can do is you can just store it in an array. So here is fib2, where I've created an array of length n, and every time that I compute a Fibonacci number, I'm going to store it in that array. So what this is going to do is if n is equal to 1, when n is equal to 1, store in the first place in that memory array, store the first Fibonacci number. So in memory 1, store Fibonacci 1. Otherwise, first check if the value is already stored in the memory. If it is stored in the memory for n minus 1, so like remember fib of n is fib of n minus 1 plus fib of n minus 2. So check if n minus 1 is already stored in the memory. If n minus 1 is not stored in the memory, compute fib of n minus 1 and then put it in the memory. Same kind of thing for n minus 2. So n minus 2 should be the value stored in memory. Otherwise, compute it for n minus 2. But this branch should not really be taken. Why not?
Because if you've already evaluated n minus 1, you would have had to have evaluated n minus 2.
Yeah, so that's generally going to be the case. So yeah, that's going to be the case.
Unless n minus 1 is 1.
Yeah, unless n minus 1 is 1 is the only other version. And then this one is just checking that we haven't caused an overflow. And that is our fib2. So let's run this one. And an interviewer in a programming interview might actually expect you to be able to do this version. So we can see that that ran pretty quickly. Let's try it fib1 for a large number. Let's do the 70th Fibonacci number. So that's running not very fast. And what about for fib2? Can it do the 70th? It does it really fast. So there's a huge difference from the memoization. Danny?
Could you do this with a static variable for the array?
Yeah, you could use a static variable as well. Okay, so that is our implementation 2. And that has runtime O of n with O of n values stored in memory. Now I've used a slightly different notation here to indicate that the bound is tight. And you'll learn more about that hopefully next semester. So we're going to call this memoization, but Danny had another suggestion as well. He's like, why are you bothering with this recursive crap in the first place? Why don't we just write an iterative solution? So back to our code over here. Here is the iterative version of Fibonacci. And so again, in programming interviews, you should be expected to be able to write this. And an interviewer might actually quiz you, why did you do the recursive solution? The reason why most people naturally write the recursive one is because it's used as an example of recursion in first-year computer science classes, despite not being particularly efficient. So let's compile fib3. And that ran super fast. Probably can't tell much of the difference between the O of n memoization solution and this solution, but this just has a loop. There's no recursion, there's no nothing like that. So fib3 should have runtime of O of n with only O of 1. So fib3 should have runtime of O of n with only O of 1 value stored in memory. So I've saved ourselves some memory and still kept the runtime improvement. Great. What if we want to run the program a million times? Ray. Danny, pass the microphone to Ray. What's the right solution if I want to run this program a million times with lots of different values?
You might as well just keep the values persisting after function calls.
Yeah, and one thing that we're noting is which of these programs is doing a good job of storing all the values?
The recursive memoization?
Yeah, the recursive memoized ones. So even though the iterative one is actually computing them, right now we already have this nice structure where what we could do is we could tell the operating system to store the stuff that we're writing to memory to disk instead and store the results in a file. We could, of course, do something similar with the iterative one, but just the memoized one naturally lends itself to that right now. What if I want to run it with really, really big numbers? Which of the solutions that we've presented thus far is the right one?
The iterative one without storing your extra variables.
Yeah, not only does it store less, but fib1 and fib2 will give us stack overflows because the stack will get so high because we'll do so many recursive calls. What if I want to run it with really big numbers? Will any of these work?
You might want a closed form solution.
Ooh, Ray knows something a little too much. You were not meant to know the answer to this one, but there is a better solution to calculating the nth Fibonacci number than all of the ones that we've seen thus far. And this is a closed form solution for the nth Fibonacci number, known as Binet's formula. So this is the version of Fibonacci using Binet's formula, which is even better than actually computing using this n-1, n-1, and n-2. You have it right there for you. And so the runtime of Binet's formula is what?
O of 1 if you assume that these operations, like exponentiation and stuff.
You're too good at this. That was a trick question. So the answer that you're supposed to give is O of 1, but the correct answer is that with really big numbers, mathematical operations aren't actually O of 1 anymore because the circuitry in your computer isn't designed for doing them in a single step. It's going to depend on the actual length of the number. And this is going to become really important when dealing with very big numbers. So what's the most efficient runtime? What's the right way of solving this problem, Ray, for numbers in C?
No clue.
What do you think? You kind of stumbled on the answer accidentally a little before.
Is it still going to be O of n?
This is a truly O of 1 solution.
Okay.
Can you think of a way to do it? Okay, here is the answer. Fib5. I have stored all the numbers, and when I run this, it will look them up. It may be cheating, but it's actually probably a reasonable solution because only so many Fibonacci numbers fit in a long, and so you might as well encode them if you're going to be doing this thing frequently. And this is the way to impress your algorithms interviewers. Show them the other solutions as well, but pull this out and describe why. So we're going to go about 5 minutes over. I'm going to push us to the end of the hour because I've got a couple of messages for us. So our final message from the class is the real solution is actually going to depend on the real problem in front of you. So just like when I was discussing with Danny, Ray, and Darcy, the different fib methods to use, they're going to be dependent on how many times do you plan on using this? What is the actual size of the integers available to you? What kinds of things are you concerned about? Designing algorithms is going to require careful thought about a variety of things, including the constraints that you're facing in terms of your ability to develop them, use them, run them, the type of data that you're getting. You're going to want to evaluate both the theoretical characteristics and the practical characteristics. And the main message from class, of course, is algorithms are fun. So the main message from class is algorithms are fun. And that is the end of Foundations of Algorithms. And we're almost done. So this is a very important message, which is stay in touch. Like, really, please do. Nothing makes me happier than hearing from my former students in whatever way. And I think now we are probably ready. I know your schedule's kinda cray, but I can't ignore the hype. I must try FOA. The handbook says 102's a special place where boys and girls can all be helped to sort their whole arrays. I'm having wicked dreams of leaving FOC. Here's Sydney Myers cry. I swear it's calling me. I'll make my mama proud. This class has got her keen. She sees her baby girl. H1, she's gonna scream. God, what have you done? You're an FOA girl and you've gone join our subject, mama. Algorithms are fun and log n's are ideal, and squared is just wrong for sorts in this heap sorting subject. I'm gonna keep on sifting down and heap sorting subject. I'm gonna keep on sifting till my heap structure is good. I'm gonna keep on sifting in this heap sorting subject. I'm up till midnight, maybe 2 hours more. John Jong's top assignment has me sprawled out on the floor, but made easy by Sasha, her lectures I recall, with content sourced from Canucks who live west of Montreal. I thank their binary trees for just inspiring me, cause all those bubble sorts charge CPUs such fees. Tried hashing every node to make a lot of keys, but hash tables aren't right to build a hierarchy. Oh, look what I've done. I'm an FOA girl and I've come to your subject, mama. Algorithms are fun and log n's are ideal, and squared is just wrong for sorts in this heap sorting subject. I'm gonna keep on sifting in this heap sorting subject. I'm gonna keep on sifting till my heap structure's good. I'm gonna keep on sifting in this heap sorting subject. 12, and now we're on the grind, where Big O and some code in C have occupied our minds. But mama, 10 a.m. Wednesdays, I know how much I'll miss this class when I'm 10K miles away. God, look what I've done. You're all FOA girls and you've come to our subject, mama. Algorithms are fun and log n's are ideal, and squared is just wrong for sorts in this heap sorting subject. I'm gonna keep on sifting in this heap sorting subject. I'm gonna soon be missing, you'll all do so much good, but I'm gonna soon be missing all of you in our subject. Goodbye to our subject. I'm gonna soon be missing. I'm gonna soon be missing.
Thank you very much, everyone.